Okay, Charlie Buser here. We're going to be doing gas homework number 2. This is me. You have to do your own. Number 1, we're going to draw a simple graph showing pressure as a function of volume. So pressure is here. Whatever word comes first goes on the y-axis. Volume. Pressure and volume are what we call inversely proportional. Inversely proportional, so the graph is going to look like this. It's going to curve. It's curvilicious. It never reaches 0 and it never reaches 0, but it keeps going. Number 2, this one says volume is a function of pressure. Volume is a function of pressure, so volume goes first, pressure, and it's still curvilicious. The most important thing is whatever goes first, that's what goes on the y-axis. The next one says pressure as a function of temperature. That means pressure and temperature. This is directly proportional. Directly proportional. That means it has to be a straight line. These are inverse, and this is directly proportional. Combined gas law, P1V1 over T1 equals P2V2 over T2. With constant temperature, we can cancel the temperature and just write P1V1 equals P2V2. And we can just take the temperature out in advance. Now, if we have constant pressure, we can have V1 over T1 equals V2 over T2, and we take the pressure out in advance. Here, we're going to take the volume out in advance. The volume comes out, it's just going to be P1 over T1 equals P2 over T2. This formula works for every single gas law problem ever, period, always. Now, sometimes something is constant, though. Now, if we had constant temperature, we could use this formula, or you could just write 273 Kelvin, which is T1, and T2 would also be 273 Kelvin, and what would happen is they'd cancel out. Or you could cancel them in advance. This formula works. Now, if something's constant, pick something. Pick a temperature, or pick pressure, 1 atmosphere. If we put 1 atmosphere on both sides, it's going to cancel, right? And if the volume is the same, if it's always 10 mLs, it's always 10 mLs, they'll cancel out. So you can use this formula always, or if you don't like to press all the buttons in the calculator, there's 3 smaller formulas. Number 8, how many nitrogen molecules are in 5.12 liters of gas at STP? This is not a combined gas law problem. This is another one of those mole problems. 5.12 liters, it's 22.4 liters of nitrogen is 1 mole of nitrogen. And let me show you how to do that with the calculator. Let's see if I can make this so that you can see it. I don't have high quality lighting here. I'm running a small operation. I'm not running a professional operation. Here we go. 5.12 divided by 22.4. 0.229 moles of nitrogen. Question 9. This is a combined gas law problem. The gas in a closed container is a constant volume. Constant volume. What is the volume? I don't know. It doesn't say what the volume is. We can either do 2 things. We can use the combined gas law and pick a volume like 10 mLs on both sides, or we can use this formula. And I think I'm going to use this formula because it's going to be easier. So to do this, I'm going to write P1 over T1 equals P2 over T2. See, I have no volume. That's because it's constant. So the pressure is this. Now, look at this crazy number. Look at this. Who the heck wants to deal with this number? 3.0 times 10 squared. You know how to do that? Let's make it easy. 3.00 times 100 equals 300. So I'm going to get rid of this. I don't like that. 300 kPa. So P1 is 300 kPa over That's centigrade. I can't use centigrade. So I'm going to say K equals C plus 273. That's a formula to convert Kelvin and centigrade. The Kelvin is going to equal 30.0 plus 273. K is going to equal 303 K. So that's my starting conditions. Now, what will be the pressure? P2, that's the question. The temperature is lowered to minus 172. Man, that's an annoying number. Oh my gosh, somewhere over here. K equals C plus 273. K equals minus 172 and 273. K equals, get the calculator out, kids. 273 minus 172. 101 Kelvin. So now we have this completely easy to deal with setup. To get this P2 by itself, we have to cross multiply. It's going to be, ready? 303K times P2 equals 300 point kPa times 101K. Now to get the P2 by itself, we're going to divide both sides by 303 Kelvin. And this cancels completely. On this side, we're going to cancel the K's, but we got to do the math. So here's how we do the math. It's going to be 300. Can you see my calculator? 300 times 101 equals, divided by 303 equals 100 point, and it's pressure, so it's kPa. And that is the answer. No big deal. Last one. At constant temperature, so let's look at my formulas. You can always use this formula, but if I have constant temperature, that one's going to be easier. I'm going to use the easy formula. P1V1 equals P2V2. 1.00 times 10 squared kPa is the original pressure. I don't like that. I'm going to change this to 100 point kPa. How did I do that? 1.00 times 100. Three significant figures. The volume is this other stupid number. What am I doing here bothering you kids? It's going to be 120 point kPa. How did I get that? 1.20 times 100, 10 squared. At constant temperature, calculate the volume. Look at that, I'm getting all mixed up. It says at constant temperature, calculate the volume of a gas. So this is actually the second. If the original volume is this and this. So let's read this nice and slow. At constant temperature, calculate the volume of gas at this pressure. If its volume at this pressure, so P1 is going to be 120 point kPa times 1,500 mLs. Now this number right here, this is annoying, right? I'm even going to write this, because it has three significant figures. But I'm going to change it to this, which looks like two significant figures. That's a frustration. I'm going to have to remember that it's three significant figures. And this is going to be 100 point kPa and V2. At constant temperature, calculate the volume of a gas at this pressure if it used to be this. To get V2 by itself, we're going to divide both sides by 100 point kPa. And on this side, it cancels completely out. On this side, just the kPa's cancel. Now, to do this math, 120 times 1,500 equals, divided by 100 equals 1,800 mLs. But we need three significant figures, so we're going to have to switch this to 1.80 times 10 to the third mLs, which honestly, it's going to get this kind of a face. I'm torturing you kids, all right? I feel bad, but this is about paying attention to the details, not necessarily about being so casual. This is a pain in the neck, but we got the right answer. All right, homework number 2 is done.